The sky you see at night is lying to you. Of the roughly 6,000 stars visible to the naked eye from Earth, none are more than 15,000 light-years away. Your own galaxy is 100,000 light-years across. Wait, that's not a figure of speech. It's simple maths. You're seeing at most 15% of the Milky Way. And the Milky Way is just one galaxy among about 2 trillion. So that's the question that will guide the next few minutes. If what you take for a sky full of stars is actually just the dust from your cosmic neighborhood, what makes you so sure that the entire universe isn't, in the same way, almost entirely empty? And if it is, if emptiness isn't the exception but the rule, how does that change your place within it? Keep one idea in mind as you hear each of the following numbers. The universe isn't full of stars with a little bit of emptiness scattered between them. It's the opposite. The universe is empty, with a little bit of matter scattered here and there. Against all odds. In 1995, a team led by Robert Williams pointed the Hubble Space Telescope at a patch of sky in the constellation Ursa Major that looked perfectly black. No visible stars, nothing. Nothing. The chosen piece was tiny. It would take about 12 million pieces like it to cover the entire sky visible from Earth. The telescope was pointed there for 10 consecutive days, collecting light photon by photon. The result, now known as the Hubble Deep Field, shocked the scientific community. About 3,000 galaxies appeared in that tiny patch of sky that everyone thought was empty. Not 3,000 stars, 3,000 galaxies, each one containing, on average, hundreds of billions of stars. They repeated the experiment in other parts of the sky. Same result, always. Wherever they wanted, if you look deep enough, there's a galaxy. At this point, you can conclude that the universe is actually full to the brim. You just had to look harder to realize that. This is exactly where the math gets mind-blowing and proves, against all intuition, the opposite of that. The observable universe measures about 93 billion light-years in diameter and contains, according to the most cited estimates, around 2 trillion galaxies. That number has been revised several times in recent years, but it still makes your head spin no matter what. Each galaxy contains, on average, about 100 billion stars. Multiply those two numbers and you get approximately 200 billion trillion stars. 2 followed by 23 zeros. Now calculate the space that these stars actually occupy. The Sun, a perfectly ordinary star, is about 1.4 million kilometers in diameter. The volume of a sphere that size is close to 1.4 billion cubic kilometers. Multiply that by the total number of stars and you get the total volume occupied by all the stellar matter in the observable universe. About 2.8 times 10 to the 32nd power cubic kilometers. A number with 32 zeros. It seems gigantic, but compare it to the total volume of the observable universe, which is about 3.6 times 10 to the 80th power cubic kilometers. A number with 80 zeros. Divide the first by the second, and you get the fraction of space actually occupied by stellar matter. About 7.8 times 10 to the minus 49. In other words, 0.48 zeros, then 780. All the stars in the universe together occupy less than a billionth of a billionth of a billionth of a percent of the available space. To visualize, shrink the observable universe down to the size of the Earth. And all its stellar matter, all the stars at once, would fit into a volume smaller than a single atom. even smaller than a single proton. And that's not even the end of the story, because an atom is also almost entirely empty. The nucleus occupies about a trillionth of the total volume. The rest is just the space where the electrons move around, never really filling anything. The matter you're touching right now, the chair you're sitting on, is built on this same principle. Almost nothing is organized precisely enough to appear solid. Let's go down to the scale of a single galaxy, ours. The Milky Way has about 200 billion stars spread across 100,000 light years. The closest star to the Sun, Proxima Centauri, is 4.24 light years away. If you shrank the Sun down to the size of a 1 millimeter grain of sand, the closest star would be about 30 kilometers away. And that's the typical density inside a galaxy, the most crowded region that exists on this scale. Between galaxies, it's even worse. Andromeda, our closest large neighbor, is 2.5 million light years away, 25 times the width of the Milky Way. And in that stretch, there's almost nothing except for a few little dwarf galaxies. But there's a deeper problem than geometry. Here, the problem of mass simply going missing. In 1933, the Swiss astronomer Fritz Zwicky was studying the Coma Cluster, a group of thousands of galaxies about 320 million light years away. Zwicky measured the speed at which the galaxies in that cluster were moving relative to each other, and since the cluster stayed together, he calculated the total mass needed for gravity to hold it all together. Then he counted the visible mass, estimated by the brightness of the stars. The difference was enormous. According to his calculations, there was about 400 times more mass missing than what could be seen. Zwicky, in an article published that same year in the Swiss journal Physica Acta, proposed that this missing mass had to be invisible, a form of matter that neither emits nor absorbs light, but still exerts gravity. He called this dunkel materia dark matter. No one believed him. Decades later, in the 1970s, the astronomer Vera Rubin, along with her colleague Kent Ford, measured the rotational speed of stars in dozens of spiral galaxies. In the solar system, planets closer to the Sun orbit faster than distant planets. That's gravity weakening with distance. Rubin expected to see the same pattern in an entire galaxy. She found the opposite. Stars at the edge of a galaxy were rotating almost as fast as those at the center, sometimes even faster. That only made sense if there was additional, invisible mass spread well beyond the visible disk, exerting a gravitational pull. Rubin, in papers published between 1970 and 1980, confirmed what Zwicky had proposed 40 years earlier. Visible matter represents only about 15% of the total mass of a galaxy. The rest, 85%, is invisible. For a long time, the alternative hypothesis, changing the laws of gravity instead of accepting invisible matter, had serious supporters. Precisely because dark matter was only inferred by calculation, never seen physically separating from ordinary matter. This lost much of its strength in 2006 with a study led by the astrophysicist Douglas Clow about an object called the Bullet Cluster. The collision, ongoing for about 100 million years between two galaxy clusters, more than 3 billion light-years from Earth. In this collision, the hot gas, which makes up most of the visible ordinary matter, slowed down abruptly on impact. But the galaxies, much farther apart from one another, passed through almost without colliding and kept going. By mapping where the actual mass of the cluster was, using gravitational lensing, the way light bends near something massive, Clow showed in a study published in 2006 that this mass did not coincide with the gas slowed down in the center, but with the galaxies that had kept going. The dominant mass had physically separated from ordinary matter exactly as predicted. A model in which dark matter, unaffected by friction, simply continued along with the galaxies. The bullet cluster remains one of the most direct pieces of evidence for the existence of a massive and mostly invisible form of matter. According to data from the Planck satellite, published in 2018 by the European Space Agency, the universe is divided as follows. About 5% is ordinary matter, which forms atoms, stars, planets, and you. About 27% is dark matter, and about 68% is dark energy. We'll get to that in a moment. In other words, for every kilogram of ordinary matter in the universe, there are about 6 kilograms of dark matter. And 95% of everything that exists is made of something we can't see, touch, or fully explain. The strange thing isn't just that it's invisible. It's that right now, billions of dark matter particles are passing through your body without ever interacting with the atoms that make you up. In fact, without it, galaxies wouldn't exist. In the primordial universe, hydrogen and helium gas were spread out almost uniformly. And ordinary matter, as it contracts, heats up, emits light, and this emission creates a pressure that hinders gravitational collapse. Dark matter doesn't interact with radiation, so it collapses freely under its own gravity. And in the young universe, it formed the first gravity wells, immense halos that later attracted ordinary matter. Like a magnet, it attracts the iron filings. Every galaxy you observe, including your own, is nestled inside a dark matter halo much larger than itself. The visible disk of the Milky Way is 100,000 light-years across, but its halo extends hundreds of thousands of light-years beyond that, with about 10 times more mass than all the visible stars combined. So, what is dark matter physically? The honest answer is that we still don't know. The most studied candidate for decades is called the WIMP, a weakly interacting massive particle. Extremely sensitive detectors have been installed kilometers underground, waiting to capture the extremely rare collision of one of these particles with a common atomic nucleus. No confirmed detection has appeared to this day. At the Large Hadron Collider near Geneva, they try to create dark matter instead of capturing it, but nothing conclusive has appeared there either. Other candidates exist: axions, hypothetical particles much lighter, primordial black holes formed in the first moments of the universe, and a more radical hypothesis, modified Newtonian dynamics, or MOND, which does away with dark matter by changing the very law of gravity when gravity is extremely weak. MOND explains the rotation of individual galaxies well, but fails to explain clusters in the cosmic background radiation. What we know for sure is that something massive and invisible shapes the structure of the universe. What we don't know is what that something is made of. Up to this point, you could think that the picture was complete. A little ordinary matter and 6 times more invisible dark matter. Then came 1998, and a discovery took the entire scientific community by surprise. 2 independent teams, the High Z Supernova Search Team, led in part by Brian Schmidt and Adam Rees, and the Supernova Cosmology Project, led by Saul Perlmutter, studied Type 1a supernova. These explosions happen when a white dwarf, the compact core of a dead star about the size of Earth, steals matter from a neighbor until it reaches a very precise critical mass. 1.44 times the mass of the Sun. The Chandrasekhar limit, calculated in 1930 by the astrophysicist Subramanian Chandrasekhar. At this point, the star explodes completely in seconds, releasing at once as much energy as the Sun will emit in its entire 10 billion year lifetime. Since this explosion always happens at the same critical mass, every Type 1a supernova reaches basically the same peak brightness, which allows its distance to be calculated with great precision. Both teams wanted to measure whether the expansion of the universe was slowing down. The expectation was almost obvious. The gravity of all the matter should, over time, slow down the expansion. In 1998, the two teams each published independently results that went against that expectation. The distant supernovae appeared dimmer than they should have. Dimmer means farther away, and farther away than expected only means one thing. The expansion of the universe, far from slowing down, is actually accelerating. The discovery was met with skepticism, but the signal only grew stronger over time. And in 2011, the Nobel Prize in Physics was awarded to Perlmutter, Schmidt, and Rice for this. So, we give a name to what is pushing space to expand faster and faster: dark energy. But to put it simply, honestly, this name describes our ignorance more than anything else. The simplest and most disturbing explanation is that dark energy is a property of space itself. That the vacuum, contrary to what the name suggests, carries an intrinsic energy. The idea is not new. In 1917, Einstein included in the equations of general relativity a term called the cosmological constant. Not because he had predicted quantum physics, but because at the time he wanted a static universe. When Hubble proved in 1929 that galaxies were actually moving away, Einstein called that constant the biggest mistake of my career. Almost a century later, that same constant seems to describe, at least approximately, what we observe today, for reasons that Einstein never imagined. Quantum field theory predicts that even the most perfect vacuum is never completely empty. It is permeated by constant fluctuations with a non-zero minimum energy. If this vacuum energy remains constant as space expands, the more space there is, the more dark energy there is in absolute value, and the faster the expansion accelerates. But here lies one of the most embarrassing problems in all of theoretical physics. When physicists calculate, based on quantum field theory, the expected value of this vacuum energy, they arrive at a result about 10 to the power of 120 times greater than what is observed. A difference sometimes called, without exaggeration, the worst prediction in the history of physics. Either our understanding of quantum field theory has a fundamental error, or there is some unknown mechanism canceling almost all, but not all, of this predicted energy. It is exactly this effect of dark energy on the future of cosmic structure that turns the void we've been talking about since the beginning into a trend, into a direction. Going back to the scale of the galaxies themselves. In the 1970s and 80s, astronomers began to map the three-dimensional position of galaxies by measuring their distance through the redshift of their light. When millions of galaxies were placed on a 3D map, a pattern emerged that wasn't a uniform distribution, like sand on a beach. It was a web, long filaments of galaxies, clusters where the filaments cross, and between these structures, huge regions that are almost completely empty. In 1981, the astronomer Robert Kirshner and his colleagues, while mapping the constellation Boötes, discovered one of these regions. A sphere about 330 million light-years in diameter, with only around 60 known galaxies where a region of that size would normally have thousands. They called it the Boötes void. Almost 99.4% fewer galaxies than expected. Since then, we've mapped many other similar voids, and we've realized that they're not an exception. In terms of volume, they are the dominant structure of the universe. And they're not temporary accidents that will eventually fill in, they're growing. Because less dense regions have less matter to locally slow down the expansion, so they stretch faster than the cosmic average. While denser filaments and clusters resist better thanks to their own gravity, Over time, the cosmic web becomes thinner and thinner, with filaments separated by increasingly larger voids. It's worth clarifying an essential nuance here. It's not the galaxies that are traveling through space to move away from each other. It's the very space between them that's stretching. Imagine dots drawn on the surface of a balloon. When you inflate the balloon, each dot moves away from all the others, not because it moves across the surface, but because the entire surface expands. The universe works like that, only in 3 dimensions. That's what Edwin Hubble discovered in 1929 by measuring the distances of galaxies using pulsating stars called Cepheids and comparing those distances with their recession speeds. The farther away a galaxy is, the faster it moves away. This relationship, now called Hubble's law, has a rate, the Hubble constant, of about 70 kilometers per second per megaparsec. From about 14 billion light-years away, the recession velocity exceeds the speed of light itself. This doesn't violate any law of physics. It's not the galaxy that's traveling faster than light. It's the space between it and us that's expanding faster than light can cross. The light it emits today in our direction will never reach us because the distance to travel increases faster than it can advance. A common question comes up here. If space is expanding everywhere, why aren't you, the Earth, or the solar system growing along with it? The answer lies in the relative strength of the bonds involved. Where gravity or electromagnetism keeps objects tightly bound, those bonds far outweigh the tiny effect of expansion at that scale. Expansion only becomes relevant between objects that are sufficiently distant and weakly bound to each other. This boundary, beyond which nothing can reach us anymore, has a name: cosmological horizon. And the most disturbing detail is that this horizon is closing in over time. As the expansion accelerates because of dark energy, galaxies that we can observe today will, one by one, cross this horizon and disappear from our observable universe forever. The universe we can see is shrinking, even as the real universe keeps growing. Our local group will remain visible. The Milky Way and Andromeda, gravitationally bound, will merge billions of years from now into a single elliptical galaxy. But everything that is not bound to us will move away forever, cross the horizon, and disappear from our sky. One day, observers in what remains of our merged galaxy will see nothing but the galaxy itself. Even the cosmic background radiation will stretch to wavelengths too long for any instrument to detect. And future civilizations will have no way of knowing that the universe had a beginning. We, on the other hand, are living right at the moment when this story is still readable. It's more a matter of timing than a position. Let's follow this thread to the end, because it shows how rare this moment we're living in is. The universe is about 13.8 billion years old today. The formation of stars, already in decline, will still continue for a long time. Current models suggest a total duration of about 100 trillion years for the so-called stelliferous era, the era of stars. We are at this moment only about 0.01 of the way there. The overwhelming majority of stars that will exist haven't even been born yet. After this era ends, no new stars will form. The existing ones will fade out one by one. The red dwarfs will shine for trillions of years until they become white dwarfs. Stellar embers the size of Earth that only cool down slowly for durations almost impossible to calculate. By around 10 to the power of 15 years, all the stars will have gone out, and the universe enters the so-called degenerate era, a scenario of white dwarfs, neutron stars, and black holes gradually moving toward total isolation. Black holes don't disappear instantly, but they're not eternal either. In 1974, the physicist Stephen Hawking showed that black holes emit an extremely weak radiation, now called Hawking radiation. And because of that, they slowly lose mass until they completely evaporate. A black hole the size of the sun would take about 10 to the power of 67 years to disappear. A supermassive one would take about 10 to the power of 100 years. Time so vast that the current age of the universe compared to them is less than the blink of an eye. Some particle physics theories even predict that protons are not perfectly stable and would take at least 10 to the power of 34 years to decay, a limit established by decades of underground experiments that, to this day, have not detected any decay. What the universe reaches at the end of this path has a name: heat death, a state of perfect thermodynamic equilibrium, where energy is spread absolutely evenly, with no difference in temperature, density, or any remaining structure, and where, as a consequence, absolutely nothing else can happen. No dramatic collapse, no final explosion. Only silence that settles in little by little and remains forever. Some more speculative models imagine an even more radical scenario called the Big Rip. If the density of dark energy increased over time, instead of remaining constant, the expansion would eventually tear apart not only galaxies and star systems, but also planets and later, atoms themselves. Most physicists consider this scenario unlikely, but it has not been ruled out. In any case, the conclusion is the same. Structure, complexity, anything that resembles an event belongs to a relatively short window in the history of the universe. A window that we inhabit right now. There remains one last question, and it's about timing, not space. Are we early or late in the history of the universe? Do the math and the answer is clear. We are very, very early. We've barely traveled 0.01 of the way. Almost all the stars that will ever exist don't even exist yet. Almost all the planets that will form haven't formed yet. And therefore, most likely, almost all the opportunities for life to appear somewhere haven't even happened yet. We exist right between two extremes. A past too dense and opaque to allow for observers, and a future so diluted and silent that no civilization would be able to reconstruct its own cosmic history anymore. It's probably not a coincidence. Life as we know it requires stable stars, rocky planets, and billions of years of evolution. Conditions that only exist within this specific window. There's one last piece missing from this picture, and maybe it's even more breathtaking. Why does the universe have exactly this level of emptiness? No more, no less. The cosmic background radiation emitted about 380,000 years after the Big Bang, at the moment when the universe became transparent to light for the first time, shows remarkable uniformity. The temperature varies by less than 1 part in 100,000 from one point in the sky to another. But these tiny variations are not just any detail. They are the seed of all the structure we observe today. Regions just a bit denser than average gradually attracted more matter through gravity, becoming even denser in a self-reinforcing cycle, until they collapsed and formed the first galaxies. The regions that were a bit less dense became the voids we explored earlier. But this amplitude of variation, 1 part in 100,000, was no small thing. If it had been much smaller, gravity would hardly have had anything to hold on to. Matter would remain diffuse, stretching out forever, never forming any stars, galaxies, or any kind of life. If it had been much greater, the collapse would have been far too violent. Instead of galaxies, the early universe would have been filled with black holes. The same reasoning applies to dark energy. A little stronger, and the expansion would have prevented any matter from coming together before the first stars could form. A little weaker, and gravity would have pulled everything back in a final collapse. The big crunch, long before life had time to appear anywhere. This is the so-called anthropic principle. We observe a universe compatible with the existence of observers simply because, in a universe incompatible with that, there would be no one to observe it. This doesn't prove any intention behind these adjustments, but it does reveal, at the very least, how delicate the balance is that allows our existence. And this emptiness that we've been measuring since the beginning of this story is not an unfortunate accident. It's the very condition for us to be here to talk about it. A denser universe would have produced only black holes. A more empty universe wouldn't have produced any structure at all. It took exactly this level of emptiness for matter to be able to organize itself into stars, planets, and carbon atoms. And then, at the end of a breathtaking chain of coincidences, someone capable of doing the math and understanding it. I have one last number to put on the table before we wrap up. The lightest elements, hydrogen and helium, were formed in the first minutes of the universe, long before the first star. But the carbon in your cells, the oxygen you breathe, the calcium in your organs, the iron in your blood, none of those elements existed back then. All of them were forged later inside the cores of stars through nuclear fusion. Elements heavier than iron require an even more extreme mechanism. The supernova explosion of a massive star or the collision between two neutron stars is violent enough to forge elements like gold or iodine in seconds, before spreading them through space as a cloud of gas and dust. This enriched cloud eventually collapsed billions of years later to form a new star, our sun. The sun surrounded by a disk of debris that became the planets, including Earth. Every carbon atom in your body passed through the interior of at least one star before it ended up here. Against all odds, organized in such a way that allows you right now to hear this sentence. You are literally a temporary arrangement of matter forged inside stars that died a long time ago. One of the rare pockets of organized structure somewhere in the universe that, as we've just seen, has almost none. I used to find that idea frightening. I'm not going to deny it. The idea that almost everything, absolutely everything, is empty, and that the matter I touch, the people I love, the earth itself are nothing more than a statistical exception drowned in an ocean of nothingness. But after coming back to it so many times, something changed in the way I see it. Because this emptiness, in fact, is not the enemy of structure. It's the condition for it. Without it, no galaxy would have space to form. No star would light up without bumping into its neighbor. No planet would be able to orbit peacefully for long enough for something like life to have a chance to appear. The void is not what prevents existence. It's what makes room for it. So maybe the right question isn't, why is there so little matter in the universe? Maybe the right question is, how does any exist at all? How, out of virtually none of the available space, something like carbon atoms ended up organizing into cells, then into organisms, and then into a consciousness capable of measuring its own rarity. You are literally the exception in a universe governed by the rule of emptiness. Not the center of anything, not the purpose of anything, just a pocket of structure, extraordinarily unlikely, that had time before the expansion scattered everything, to turn around and look around. So the next time you look at the starry sky, thinking it's full, remember what you know now. What you're seeing is almost nothing, surrounded by emptiness that the human mind is not well equipped to imagine. And even so, that almost nothing was enough. It was enough for you. That's not comforting in the easy sense of the word. But it is, I think, the closest thing there is to a form of peace. Knowing exactly how rare you are, and choosing even so to keep looking. I always go back to that calculation from the beginning, that infinitesimal fraction, that infinitesimal percentage with 48 zeros. In the beginning, it crushed me. Today, it calms me down in a way that I have trouble explaining any other way. Rarity doesn't take anything away from the reality of the rare thing. A single lit candle in a completely dark room isn't almost nothing just because the darkness is all around it on every side. On the contrary, it's the only thing that matters in that room, exactly because of the darkness around it. The contrast doesn't diminish the light, it reveals it. It's this candle, unlikely, temporary, surrounded by emptiness beyond comprehension. And yet here, burning bright, listening to this sentence all the way to the end. And then,